we've been doing a lot of approximating of functions, and we've been using tangent lines. We used either one tangent line approximations, or we've done Euler's method, which is multiple tangent lines. And the tangent line approximates the function pretty accurately if you zoom in close enough. But we know that the further we get, the further your approximation ends up relative to the actual function value. And you can try to fix that by doing multiple lines. You know, with Euler's method, you go to another line, you assume the derivative, and then you assume the tangent line starting there, and you get to another line, and you get closer, right? But we're still just using lines, okay? Better than, 2 lines are better than 1, 4 lines, of course, are better than 2, but we're still just using lines. And these functions have curves. So what we need to do today is we need another way to approximate this function. You know, and this is some crazy function. I just want to be able to approximate it better than how I've done it so far. And I want to kind of use the fact that these functions have curves. And we're going to approximate not only tough function values, so like, you know, polynomials at a decimal, but also tough functions like e to the x, sine x, cos x, where it's like I could not even guess what the sine of 0.1 is close to. I can't do some calculation on a piece of paper to come up with it. I'm kind of stuck, okay? So let's pretend we have some sort of crazy function. This is some sort of crazy f of x. It's not a polynomial. It's, you know, some type of sine or cosine variant, something like that. And I want to see if I could maybe mimic the function at a location. Instead of necessarily just going like that and saying, okay, that's good, could I maybe come up with some sort of x squared that maybe is not even that poor, is like this. And all of a sudden, if I can kind of match the curve at a certain interval, I could approximate these values. Maybe I could do even better and, you know, have it like that. Well, that's pretty good. Well, maybe I can even go further and look at some sort of x cubed, which can follow kind of my graph like that. Maybe I can have something that ends up just falling on here, and it's something to the 4th power and goes like that. That would be really, really effective ways to approximate this function value. And I'm not using lines. I'm using, you know, these polynomials. You know, this might be a 4th power, 1 hump, 2 humps, 3 humps. And all of a sudden, we're looking pretty good with our approximations. Okay? So that'd be pretty interesting. Well, let's go ahead and see kind of a thought process to do that. Okay? So let's try to approximate this f of x and go ahead and start drawing this f of x multiple times. We'll be doing it a bunch. And we are going to approximate the f of x, which is not a polynomial, some crazy function, maybe a version of sine or cosine or e to a power or log or something like that. But we're going to use a polynomial to approximate it. We're going to denote this polynomial by p of x. But we need a specific location. We can't just start drawing crazy things anywhere, okay? We're going to try to focus on a center, okay? A specific point, or at least we know, let's start here and make sure that that is completely accurate, okay? So we are going to focus or center our approximation at C. This point in red right there. And I'm telling you that f of c is a. So that is a value that I know. F of c is a. Above all else, we want to make sure that whatever kind of crazy thing I end up coming up with, no matter how it looks, no matter what happens, above all else, we need to make sure that we have this point in our approximation. If f of c is equal to a, we want to make sure our p of c is a. Okay? Well, we've just come up with a polynomial approximation for f of x. We have a y equals a approximation. What does that look like? That looks like a straight line. So I could say, okay, p of x equals a. This is, my simplest approximation. Of the function centered at c. Okay? Now, does it do well anywhere else? No. But at least we know it nails one point perfectly. Okay, but let's go a little bit further. Let's kind of work with, our concepts of derivatives to understand, maybe some other things that we could be doing. So maybe let's give it another thing that it matches. Let's make sure that the first derivatives of f and p match. Okay? So let's say f prime at c is equal to b. Okay, we have the point matching. Now let's just make sure that the first derivative matches. Well, if p of x equals a, which gives you that point p of c which equals to a, does this derivative give me p prime of c equals b? What would be the derivative of just a if a is a constant? It'd be 0. Okay, so p prime, if we were just using a, is 0. So we need to adjust things. I want p prime of c to equal b. All right. What can I add maybe next to the a to make sure I have the derivative p prime at c being equal to b? What maybe can I put next to a? Discuss with your neighbors what you think you could put next to a so that its derivative, our polynomial approximation at c equals b. Think polynomials. So we're going to add something maybe with an x. Discuss. Figure it out. It's not that hard. I want p prime of c to equal b. P of x is equal to a. That means p prime of x is 0, so this is not going to work anymore. I need something else so that the derivatives match. What should I put next to the a? Anybody? bx, great idea. Phenomenal geniuses. Okay? All right, great. So now I got p prime of x is equal to b. All right, because A goes away, BX goes. So that means P prime of C is equal to B. Hooray. Wait, there's something wrong. Hold on a second. We're not geniuses. Above all else, our approximation needed to have what occur? Above all else, we need to make sure that P of C equals A. So I do have my derivative that is correct. However, if I looked at P of C, I need to get A, but I get A plus B times C, which is not just A. So good idea, but we need to change this up a little bit. See if you can figure out what we can change this to be so that P of C is just A, and the B times C goes away or just ends up not being there at all. And our derivative is still B. This one, if somebody figures it out, just let me know. Anybody? I'll give you a hint. If we use parentheses around the x, and maybe we put something inside the parentheses next to x, we're going to be able to have P prime still be B, but P of C still be equaling to A. Anybody? Yes, very nice, the Cilliers. If we did P of x is equal to A plus B times x minus C. Well, let's check. Do we get P prime is equal to B? Yes, the derivative of the x minus C, you can really think about just distributing that, and that would just be B. So that means P prime of C is equal to B. Check. And P of C would be A plus B times C minus C, which is just A. So that's good. Fantastic. We have now created a new polynomial. P of x is equal to A plus B times x minus C, and it looks like this. It's our tangent line. Okay, great. But again, we're still dealing with lines. Now let's move further, and let's start giving our polynomial approximation some curves. Let's make sure that the second derivative of f matches the second derivative of our polynomial approximation. Let's make sure that if f double prime of C, and I've already used A and B, let's skip over to D. Okay, if f double prime of C equals D, let's make sure P double prime of C equals D. Okay, now let's go back to our previous approximation, which was A plus B times x minus C. Does the second derivative equal D? No. P double prime would end up equaling 0, right? P prime equals B. And then P double prime is going to equal 0. So I'm going to need to adjust. And I'm going to have to add something else. I got A plus B times X minus C, which is going to work out. But what do you think we'll need so that we have a second derivative that is not equal to 0? What type of expression? Polynomial expression. I got an X. If I took the derivative of anything with X's, it ends up being just X to the first power ends up being 0, right? As long as there's an X to the first power, it's going to eventually get 0. But is there another version of X whose second derivative is not 0, whose second derivative is a value? X squared. Good. Let's add some X squared. Now, if I have this X squared and I plug in C, am I going to get P of C is equal to A? No. Again, if I do this with just the X squared and I plug in C, well, I'd get A plus, this ends up being 0, but this would be C, C squared. Okay, so that's not A. So I don't want X squared, I want what? Ms. Cilliers? X minus C squared. Fantastic. Okay? And what do you think we should put in front of here so that our second derivative is equal to D? D, right? Makes so much sense. Geniosos. Fantastico. Well, let's check to see if this is correct. Now we got P of C still equal to A. Everything else cancels because you got X minus C, so C minus C. And if I took the first derivative, let's see. First derivative of X would be 0 plus B plus, what would be the derivative of this? Right, 2D, and then X minus C. Now, that means the first derivative at C is still just going to be B, right? Because this C minus C is 0. That goes away. Fantastic. So this works. This is still good. But what about my second derivative? What happens? What do I get? 2D. So that means my second derivative at C is 2D. Is that what I wanted? No, what do I want it to be equal to? Just D. So this is wrong. Not Geniosos. Adjust. What should I do maybe to this so that I don't have 2D, I have just D? Right, maybe take that D and divide it by 2. Phenomenal. Now, if I checked this, the function value at C checks out. It's A. That's what I want it to be. The first derivative is B times B plus D times X minus C. Well, the first derivative at c is still b. That's still good. And then if I look at my second derivative, I would just get now d. That works. So we have just found a nice curved approximation. And all of a sudden, if I look at this, since it's got an x squared, we're going to see that instead of a line, we're going to have something that's going to look like that. All right, well, let's make sure the third derivatives are the same. We already did A, B, C, and D. Let's move on to E. Let's say that f, this polynomial that we're approximating, its third derivative at this value C was E. Now I want, along with everything else, the third derivative of my polynomial approximation at C to equal E. We'll try our last one again. A plus B times x minus C plus D over 2 times x minus C squared. Its third derivative is 0, so we need to adjust. All right. What do you think we should add on to this polynomial so that its third derivative is E, and its second derivative is B, and its second derivative is D, and its first derivative is B, and it has the point CA. Faciliers, we're going to assume there's a what minus what to what? Yes. And that is good because if we have an x minus c to the third, P of C will still equal A. Hooray. Now, do you think we're just going to have E here? No, we figured out from the last time when we used D that just having that's not going to work. Another idea. Yeah, E over 3. Perfect idea. Let's try E over 3. Okay? Well, here we go. P of C is equal to A. P prime is B times, sorry, keep doing that. P prime is B plus D times x minus C plus, oh, that 3 and that E goes away, so it ends up being just E. Fantastic. X minus C squared. So that means P prime of C is still equal to B, because that goes away and that goes away. The second derivative ends up being D plus, you probably see that something's wrong here, because I got this 2E here. This 2, the 3 that changed and went away, which is great, all of a sudden turned into 2. The 2 came out in front. The second derivative actually works. The second derivative at C is D, but now my third derivative ends up being 2E, which is not what we want. So, what do we need? We need E over 6. This is exactly right. So we got to adjust more, but I'm not going to write it as 6. I'm going to write it as 3 times 2. Okay? This works. P of C ends up equaling A. P prime of C ends up equaling B. P double prime of C equals D. P triple prime of C will equal E. All the things that need to match up with F. And what we would find is that we'd have some cubic, maybe that looks like this, and is matching my curve even more right around C. Now, I want you guys to try something. And I want you to guess what the next term would be if the fourth derivative, and once we get past 3 tick marks, we use parentheses and the number. This stands for the fourth derivative. If the fourth derivative of f of c was the letter f, what would be the next term? Go. We know it's got to be x minus c to the fourth. I know I'm going to have f somewhere. But figure out what goes under f. So that the fourth derivative is f. Nice. Can we get it over here? Nice. Excellent. Not enough, but that works. That's not going to work, unfortunately. My advice for those where it's not working is to think about why I wrote this as 3 times 2 instead of 6. Excellent. If you have 12, it's not it. What do you have, Mr. Quigley? 4 times 3 times 2. Let's think about it. If I took the derivative 1 time, I would need the 4 to go away. Okay. Put a 4 there. But if I just had a 4, then I'd have 3f squared and then 6f, and that's not f. So we got the 4 down. Well, I need that 3 to get rid of the 3 when I subtract this and go from 4 to 3. So now I have, boom, 4 cancels. And then when it comes to a third, and then I'll bring that down to take that derivative, and that 3 cancels. but then I'd still have an x minus c squared, and then I'd take the derivative of that, I'd have a 2f. Don't want that. So I also need a 2. And that works. Now, what's going on here? What if I said that the fifth derivative was g? Could you write the next term? Go ahead, write the next term. Well, you probably figured out that you need a 5 times a 4 times a 3 times a 2 down here, so that the fifth derivative of my p of x gives me g, right, when I plug in c. And that's fantastic. Now, there is something in math where we have this kind of idea where it's a number times the previous number times the previous number. You know, it's 4 times 3 times 2. If I really wanted to, actually, I could have put a times 1 right there, right? If I wanted to right here, I could have put a times 1 right here, times 1 right here, times 1 right here. What is that concept where we're multiplying all the whole numbers until we get down to 1? A factorial. All of a sudden, this factorial shows up. Okay? And if we wanted to write this as like an nth term, you know, let's say our fifth derivative or our nth derivative of c is just what it is. I'll just leave it at that. What would I write? I would say it would be the term would be plus whatever this is divided by what? N factorial times x minus c to the nth. And what we would continue to see is better and better approximations, and we'll see this once we start doing it with actual functions, that sometimes will actually be such good approximations, we'll say it's equal to the exact function. Sometimes we'll say it's a great approximation only on an interval. Don't go beyond the interval, okay? Depending on how many terms we're using, we'll see that, okay? And this is where things get tricky, is like, oh, is it going to, when n approaches infinity, are we going to just have the same function? No. If you look at e to the x, we'll see that the more terms we use, the closer and closer it is to be the exact function. But if we look at something like this one, this is a good one. This is the log of 1 plus x. We see that if we use 8 terms, 9 terms, 10 terms, 15 terms, 20 terms, 45 terms, 100 terms, are we getting closer and closer to being on top of the exact function? No, but we are exactly on the function at a specific interval. You see, all of a sudden, after 1, our polynomial approximations, its end behavior does not match the end behavior of this function, okay? So for certain functions, it ends up going to be extremely great. We're going to have such a good approximation for the entire function. and we can say it's equal to. So for other functions, we're just going to look at a specific interval, a radius, where our approximation is going to converge with our actual function. And we get into that in the future. Okay? But what these are called, what we just kind of generated, is a Taylor polynomial to approximate functions. Okay, we denote it by P of x, and it's usually to approximate f of x centered at f of centered at x equals c. We'll say it's our first value, f of c, which we said was a, plus our derivative at c, which we said was b, times x minus c, plus our second derivative of c over 2 factorial times x minus, oh, why did I do a? It should be x minus c. This is where we're centering, just like we did it. In some books you'll see c, in some books you'll see a. Okay? This would be x minus c squared plus our third derivative over 3 factorial x minus c cubed. I'll do, 2 more just for the sake of it, plus the fourth derivative, which we'll denote by parentheses in the 4, of c over 4 factorial, x minus c to the 4th, plus dot, 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 plus we'll do the nth. Our nth derivative at c over n factorial, x minus c to the n. We will say that this p of x approximates f of x extremely well around c, but possibly it approximates the entire function extremely well for the entire function. We'll be able to figure that out in the future. Okay? Now, for all these, we've kind of been looking at a specific location that is, off to the side here, this x equals c, on the x-axis. A great location to do these approximations is at x equals 0, when c equals 0. So it's a specific situation that we will call a Maclaurin polynomial or Maclaurin series. It's when we are centered at 0. Well, what would that look like? We'd still say it's p of x. It's still a polynomial approximation. But instead of f of c, f prime of c, f double prime of c, instead of having x minus c's all the time, it would just be zeros. Be f of 0 plus f prime of 0 times x minus 0. Well, don't write that, just write x. Plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 x cubed over 3 factorial plus dot 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 plus the nth derivative at 0 x to the n over n factorial. We call this a Maclaurin series. This formula here, magic pen, happy faces, you need to have, essentially memorized. It's not something that I want you to memorize. It's something that we work through the process of generating it, so it should make sense to you. We want to make sure that the point is shared, that we at least know that regardless of everything else, if I plug in 0, I have the point on f at 0 that I'm approximating. And this is used to approximate f. Then I want to make sure that the first derivative is going to be the same. So if I have the first derivative at 0, that works out. We said that, we used a, we used b, because sometimes when you have f's in, you don't understand that we are using f to approximate itself. We have to know some stuff about f so that we come up with a polynomial approximation. And the stuff we know is the derivative and a point. If we know a bunch of derivatives and a point, we can approximate the function very well. So we use itself to approximate it, all by just looking at its derivatives. That has to be understood and memorized. This has to be understood and memorized. Very important. Okay? Now let's see how powerful this can be. Now, notation, this p sub n would be the nth degree polynomial approximation. Nth degree Taylor / Maclaurin polynomial. Taylor and Maclaurin were mathematicians who came up with these things. So if I ask you to find p sub 4 of x, you're going to want all of your terms up to the x to the 4th and stop there, which will be over 4 factorial, and you'll have some, 4th derivative of x at the point, maybe 0 or whatever, okay? So that's where you stop. That'd be the 4th degreed Taylor polynomial. Okay, we are going to find the approximations, the Taylor approximations for e to the x centered at 0. This would be the 0th degree, which would just be the points, 1st degree, 2nd degree, 3rd degree, 4th degree, and then nth degree. But at least we'll go 0, 1, 2, 3, 4. Okay, now we have the function. Now, do I know what f of 0.1 is? No, I don't know what e of 0.1 is. But maybe we can come up with a polynomial that I can use a very basic calculator that does not have any e functionality to it, but can maybe, take things to a power and multiply things. If I use a basic calculator, let's see if we can come up with a polynomial approximation to approximate this e to the 0.1. Okay? Let's get to here by generating all 3 of these, all 4 of those. Okay, so we are going to find p sub 4 of x. Well, I first need my formula. It's always going to help me. Now I'm centered at x equals 0. It's very, very important to see, understand. That's my center. That's my C in my formula. So that means I'm using a Maclaurin. The Maclaurin is just a version of the Taylor. It's just with zeros in everywhere. Okay. So I got f of 0 plus f prime of 0. If you're not sure when to start the factorials, you can always use 0 factorial and 1 factorial, and it actually works. 0 factorial is 1, 1 factorial is 1, And then you could start on the second derivative. 2 factorial. I need an x here. I need an x squared here. Third derivative at 0, I need an x cubed. And then my fourth derivative at 0, x to the fourth. Okay, this is just your general form of this polynomial approximation for any function. Our function's e to the x. All we need to do now is fill in the derivatives and fill in the point. What's f of 0? If f of x is e to the x? 1. Okay, good. What is f prime? Any derivative of e to the x is itself, right? Okay, so what is the derivative at 0? 1. Good. So f prime of 0, e to 0 is 1. So this becomes plus x. This will be 1 over 1 factorial. Plus the second derivative. Well, the second derivative is e to the x. The second derivative is 1. So this is x squared over 2 factorial. Third derivative is 1. And the fourth derivative is 1. Very simple. We're saying that this polynomial is going to approximate e to the x around 0. Very simple how we generated it. We just looked at the derivatives of it and a point. Well, get out your calculators, graph e to the x, and graph this polynomial. Now, this is the fourth degree Taylor polynomial. This would just be, the 0th degree. If I looked at the first 2 guys, this would be the first degree, okay? If I looked at the first 3 guys, you guys get the picture, right? This would be the second degree, p sub 2, et cetera, okay? So when I'm asking you for the 4th degree, you don't just write the 4th term or the 5th term with the x to the 4th, you write all of the terms. This would be the 4th degree Taylor polynomial. Fantastic. You guys know how to do factorials in your calculator? Go to math, over to PRB, probability, and there's the factorial, which sometimes might help. Fastest growing function except for what function? Yes, n to the n, right? And here's e to the x. And then we have this fourth degree that, man, it's like right on top of it, right around 0. Okay? Fantastic. Now, back in the day when calculators did not know how to calculate e to anything, you could type in 0.1 and multiply it by itself and divide it and see how close an approximation we can get to the actual value of e to 0.1. So I'd like you to type in p of 0.1 and compare it to e of 0.1. In graph trace?
No, you can do second calc, and then do value, and then second.
Right. You can do trace and do the same thing. So 1.10511709. If I go up, I got 1.10511708. We are accurate to, what, the 8th decimal place, 7th decimal place. I think I added extra decimal place over here, though, so I'm going to do it here, too. Okay? Pretty fascinating that now that we're just matching up derivatives and making sure that our point is the same, our first derivative is the same, second derivative is the same, third derivative is the same, fourth derivative is the same, we have an incredibly great approximation tool. Okay? Let's do the same thing for sine of x. Let's get to the fourth degree Taylor polynomial. So the Maclaurin polynomial, since we're centering at 0. Oh, and there's one thing that we forgot to do. Forgot to write the nth degree. The nth term would be x to the n over n factorial. Please do that for e to the x. So that should be probably at the end plus dot 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 plus x to the n over n factorial. It's not equal to that. really interesting when you go through and look at the derivatives and you look at the function value at 0, is that you get 0 plus x plus 0x squared over 2 factorial, which is just 0, minus x cubed over 3 factorial, plus another 0x to the 4th over 4 factorial. We can go ahead and assume, and we'd be correct, that we would end up being adding an x to the 5th over 5 factorial. So really, what ends up happening is that there is no 4th degree Taylor polynomial for sine of x. We would have to understand that there's the only odds that have derivatives that would have a degree. Now, as an exercise, we should practice writing out the nth degree term of this Taylor polynomial. I'll give you one more. If we did the 7th degree, we'd end up with a minus x to the 7 over 7 factorial. Can you write the nth term? Go ahead and try. Depending on if you start n with 1 or 0, it all depends on how it would be written. But you need some negative 1 to a power that will change these signs. You'll need x to an odd power, either 2n plus 1 or 2n minus 1. If I start with 1, then 2n plus 1 will work, but then this would have to be n plus 1 here, or n minus 1. And then over, I need an odd factorial, so 2n minus 1 factorial. Okay? Now, let's go ahead and see. Let's just use the 5th degree. Not go any further. Why don't you graph this and graph sine of x, see what it looks like. See, does this do a good job of approximating sine of x around 0? Man, that's phenomenal. Isn't that phenomenal? I kind of want to I want to instant replay with a little circle so that I can see it. All by matching up derivatives. We get something that just is right on top of this guy for a long time too. And then it leaves it, it's got some end behavior it has to attend to, but right around 0 and looking, a lot further than we could look using tangent lines. We're right on top of it, right on top of it. And back in the day when we didn't have, calculation tools to give us values of sine, we literally could do this. And all of a sudden we could press, on our home screen, 0.1, if I want to approximate sine of 0.1, 0.1 minus 0.1 cubed divided by 6 plus 0.1 to the 5th divided by, divided by 5 factorial. And then we go sine of 0.1. And we see, holy cow, how great of an approximation is that? All by just matching up derivatives at a certain point, we get this powerful thing. Okay? What we probably should do is rewrite it as a series, as a sum. We could say, and we should do this for e to the x as well, that p of x is the sum of x to the n over n factorial with n starting at 0 and going to infinity. That would be going to whatever number. If we're going to the 4th, we'd say p to the 4 would be 4. Okay, and then for this one, we would say P5 of x would be the sum -1 to the n plus 1 over x to the 2n minus 1 over 2n minus 1 factorial, and is starting at 1 and going to 5. No, it's going to 3. Now, make sure we have these down. Why did I say 3? You're not going to 5, because if you went to 5, you'd have x to the 9th. That would mean we'd have the 5 terms. We have 3 terms, and we already jump up to the 5th degree Taylor polynomial. That's because the derivatives with the zeros skip some terms. Okay? So that's good. We're also going to do the same thing with cosine. So let's do one more. And let's find, hopefully, the 4th degree Taylor Maclaurin polynomial for cosine, centered around 0. Nice. Okay, we notice that same sort of oscillation that we had with sine, cosine's approximation ends up being with the even powers. And go ahead and attempt to write the nth term for the cosine approximation Maclaurin polynomial. I would write it as x to the 2n if I started n at 0. I'd do x to the 2n minus 2 if I started n at 1. All depends on things. And then this would be 2n factorial. Understanding that 0 factorial is 1. Yeah. Oh, right. Thank you. I forgot about the negative 1 to the it has to be a n plus 1. If we're starting at 1, why don't we just start at 0? Okay? And we can do the same exercise of graphing it, seeing how well it mimics it, depending on how many terms we look at for these, and see that it's a great approximation. I want to do one more for a reason, because these approximations, these Taylor/Maclaurin polynomials that we're generating for these 4 functions, we kind of have to memorize. It's not something that we really have to memorize. It's more of just having the understanding of the Taylor formula, where it came from, and then kind of understanding that there is a relationship, at least between 3 of them. Okay, so let's try it. 1 over 1 minus x. For its derivatives, I'd like you to rewrite this as 1 minus x to the negative first. That's going to help you. And let's just go to the 4th degree Maclaurin polynomial and write the nth degree to this guy. Notice that the derivatives are not just, ones and zeros this time, the negative ones. Derivatives are changing. We get first function value is 1, and the first derivative at 0 is 1, the second derivative of 0 is 2. How did I get that? I, have the ones canceling. Remember, I'm just using the chain rule. The derivative of the outside, the negative 2 comes down, and then I subtract 1 and a negative 2. 1 minus x to the negative third, but times the derivative of 1 minus x, which is negative 1. So that just gives me positive 2. And then this one, I end up with negative 6, 1 minus x to the negative fourth times negative 1. That gives me 6. Then that 6 gets multiplied by the negative 4 to give me negative 24. 1 minus x to the negative fifth times negative 1, giving me 24. Okay? And if you wanted to write it all out, you'd say this approximation is 1 plus x plus 2x squared over 2 factorial plus 6x cubed over 3 factorial plus 24x to the fourth over 4 factorial. But would you leave it like that? Yep.
When you took the second derivative,
Yeah.
multiply negative 2 by negative 1, which you get 2 times 1 minus x.
Yep. Positive 2 times 1 minus x to the negative third. I have this negative 1 here. So at 0, I got positive 2. One to the negative third is just 1.
Yeah.
So negative 2 times negative 1, 2.
So like, when you took the second derivative,
Yeah. This is my second derivative right here.
so you multiply that negative 2 by the negative 1, right?
Yep. I didn't simplify it, but I just found it at 0. Right? Because we're finding this centered at 0. 0 is important because we're finding the second derivative at 0. Okay? Why would I not leave it like this? Yeah, because turns out the 2 and 2 factorial is the same thing. 3 factorial is 6, and 24 is 4 factorial. So actually, this approximation is 1 plus x squared plus x cubed plus x to the fourth. This is interesting. The others are interesting if you look at them together. Why is this interesting? If we looked at this, and we got that. Anybody make the connection? If we remember a geometric series whose sum, starting from 1 to n of 3, 1/2 to the n, we said, and we could list this as, 3/2 plus 3/4 plus 3/8, right? Where this is times a half, this is times a half. What did we say the sum was equal to if we went to infinity? If we remember from last unit. Our first term over 1 minus our common ratio, right? It'd be, 3. Well, if we look, we have this function. We're using this understanding that I'm multiplying by x every time. and I say, okay, this is a geometric series, I can just write it as that. That would be the sum. These Taylor series are fairly crazy if you really start looking into them. We won't have to go super far into them. However, there's lots of questions asked of us, okay? Before we get into some of those questions, let's recall, because we have to remember, we have to, I'll put in quotes, memorize that if we want the approximation for the e to the x, and we'll talk about what happens with this in the future, we know that the polynomial approximation is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. If I have sine of x, we'll talk about this in the future as well. We know sine of 0 is 0. That's why I know I start at 0 and I pick up at a positive x, and then I'll have another 0, and then I'll have an x cubed. It'll be negative because of the derivatives flip-flopping. And then I'll have another 0. I'll have an x to the 5th over 5 factorial, etc., etc., etc. You need to have that memorized. If I look at cosec, we'll talk about this symbol in the future. I know that the cosine of 0 is 1. I know I'll have a 0 in between, and then I'll have my negative x squared over 2 factorial. And then a positive x to the 4th over 4 factorial, etc., etc., etc. And then finally, you'll need to know that 1 over 1 minus x is approximately, though we probably should know that that's not true necessarily, 1 plus x squared plus x cubed, etc., etc., etc. You should be thinking geometric for this. What's fascinating is relationships between e to the x and sine and cosine. They're using the same terms. This has got them all. This has got some of them just alternating. This has got the other ones just alternating. Though it seems like they're completely unrelated, e being 1 plus 1 over x to the x as x approaches infinity, used a lot in compounding interest, exponential growth situations, growing with respect to its own size. And then we talk about trig functions, which is talking about unit circles and ratios of right triangles. We actually find that there's relationships between them. And this is when math starts to really blow people's minds. And this is when things get really complicated and you start diving into that stuff. And if you decide to study math in college, good luck to you. But we don't have to get into that stuff. You need to be able to generate this stuff. You need to be able to understand how we generate it, where it came from, how we got to our Taylor formula, how we got to our Maclaurin formula, because we're just matching up, things that we know on a function. A point, its derivatives at a point. We just know a lot of information about the function at one point. But using that lots of information at that one point, all of a sudden we have, these beautiful approximating functions that can do a really, really good job of approximating the function, possibly on an interval, possibly for the entire thing if we use enough terms. And that's what we're doing for the rest of this unit, is talking about these approximating functions and kind of diving deeper into them. We're not going to go super complex, but we will do some stuff. I have some more problems that I'm going to do on the video that actually we'll probably do those problems at the beginning of next class, because they're not going to be super important for your homework, but they'll be important for your quiz. All right, so here you go. Here's your part of your homework. Just a few points, parts from these questions, and then a couple book problems of generating some derivatives, some Taylor Taylor polynomials and Maclaurin polynomials.